Hello, class. Yes, that last lecture was the delta y conversion rather than the y delta conversion. And I realized how I did. I was looking back at my notes and I saw that your book did the delta y conversion first, and that's I think why I did the y delta. It doesn't really matter because I'm going to use that. A great trick of mathematics that they use, and we're going to look at this. We're going to because this is actually off. Notice how I put this. Is it called the mnemonic? I don't know what it is. Enlighten me in the comments. It's a figure. It's a figure that you use just like that Beer and Johnson's figure. Anyway, um, let's go back to this. So what I want to look at is I want to look at R1. We've got the fig, I went back and I derived this R1 equals R sub C times R sub B over R sub A plus R sub B plus R sub C. And of course, I did that showing you how you would do that on here too. Now what I want to do is I want to go the other way to get the conversion. And so I'm going to look at a mathematical identity. And that's what we're going to do through here today. So I've got R1 times R2 plus R1 times R3 plus R2 times R3. I want to look at how that works over here. Now, let's do the first one, R1 times R2. R1 times R2. Well, I think everybody can see that on the bottom, that's going to be R sub A plus R sub B plus R sub C squared, right? Because we're multiplying the denominator and we're going to multiply the numerator. So what we've got here is now R sub C times R sub B times R sub A, R sub C. So you can see that the R sub C's are going to be squared. So we've got R sub C squared, R sub A, R sub B. All right. Now let's add the next one. I think everybody can see that the denominator is going to remain the same all the way through. In fact, what I could do is I could just extend this because that denominator is going to stay the same, RA plus RB plus RC, the quantity squared, right? Let's just do the top ones now, R1 times R3. So now I've got R sub C and R sub A, R sub B. So you can see R sub B squared, so plus R sub B squared, R sub A, R sub C. And the last one we're going to do is going to be 2 and 3. And you can see common to them is R sub A. So it's going to be R sub A squared, R sub B, R sub C. Right? Does everyone see what I've got up there? I think, everybody can see what we have. Now, of all of these, I can take out of there R sub A times R sub B times R sub C, can't I? So let's simplify this a little bit. So where can I don't want to write that over again. I'm going to just write it down here, right? So this is just a continuation of this. I maybe could draw a line, but maybe I'll do that after I put the next thing in so I know exactly where to put the line. All right, so I'm going to put an equal sign down here. And on the bottom, again, we have R sub A plus R sub B plus R sub C squared, right? Now, what I want to do is I want to take out R sub A, R sub B, R sub C on the top out of every single one of those. So I think you can see what I've got left there. That's R sub C, right? Because I've taken R sub A, R sub B, and one of the R sub C's out of there. So that leaves me with R sub C. And when I go to the next one, that's going to be plus R sub B. And the next one is plus R sub C. Where have I seen that before? That's right. That means, Scott, get your red pen out and mark that out as well as that 2, right? Because those cancel out. And then what I end up getting is the product R sub A, R sub B, R sub C divided by R sub A plus R sub B plus R sub C. See where mathematics comes in so handy? So the product of R sub A, R sub B, R sub C in the numerator, and the sum of R sub A plus R sub B plus R sub C in the denominator. And so that tells us what this equals. And I just want to write that down again. R1 times R2 plus R1 times R3 plus R2 times R3. And we should put a box around that because that is such an important transient equation, right? Now, what I want to do is I want to take these three equations up here for R1, R2, and R3, right? Because we've got R1, R2, and R3 equations up here. And I'm going to divide this by those. I'm going to divide this by those. All right? That's what I want to do. Now I've got these backwards as far as the sides go because I wanted to originally use this one up here, but I can't really do that. But you know, we're in college, and math can go either way on the equal sign. Yep. So let's divide both sides by whatever their thing is. Let's do it with R1 first. If I was to divide R1 out of here, right? What would I get on this side? Well, let's do that. So I've got R1 times R2 plus R1 times R3 plus R2 times R3, all divided by R1. All right? Now, let's take the other side of the equation. Let's divide that by the other side of this. Right? Well, R sub A plus R sub B plus R sub C divided by R sub A in the denominator, R sub B plus R sub C is going to cancel those two out, isn't it? And if I'm dividing this by this, R sub C and R sub C and R sub B are going to cancel out, right? So all I have left on that side is R sub A. So R sub A equals the sum of these three different resistance pairs divided by R1. Does everyone see that? Mm-hmm. Now, where do we get that from on the schematic here? Well, look at R sub A. R sub A is perpendicular to R1, isn't it? So, if we're looking to find R sub A, we're going to use the sum of the products of the resistors divided by the resistor opposite to R sub A, which would be R1. Does everyone see that? All right, let's apply that to the next one. So if that's R sub A, then R sub B would be R1 times R2 plus R1 times R3 plus R2 times R3 divided by, what's opposite to B? Opposite to B is 2. So R2. Everyone see how that works? And so we have one more then. We want R sub C and R sub C just like before. R sub 1 times R sub 2 plus R sub 1 times R sub 3 plus R sub 2 times R sub 3. And all of that divided by the opposite of C, which is R3, right? Everyone see how that works? In fact, those, since they are in fact, I put those in blue, so let's put the opposite ones in blue as well, right? There we go. And we have all three of our equations. In fact, all six of our equations, so that we can transform either way. We've got the delta to y conversions up here, and we've got the y to delta conversions down on the bottom. And I think everybody can see how those all go together and how they come out of the figure, the schematic that we have up there. Now, that brings us to how are we going to use those equations, and what would we use those equations in? How would we really do the transformation? Now, I want to do a transformation, right, where we're using, we're going to go from a y to a delta. So let's, and I'm going to, this is a special case, right? This is a special case where all of the three resistors are the same. So I'm going to make all of these 1,000 ohm resistors, right? So if all of these are 1,000 ohm resistors, then how would I go to the delta configuration? And what would my resistors be in that delta configuration? How would I figure that out? So it's sort of, we're just doing a very simplified example problem, you might say, for this. So 1, 2, 3, 4, 1, 2, 3, 4. So how would I go from the other one? What is R sub A? What is R sub B? I probably should have put the R's in there. What is R sub A? What is R sub B? And what is R sub C? Right. And then over here on this, we know that this is number 1 resistor, and this is number 2 resistor, and this is number 3 resistor. You'll get that down, you know, A, B, and C, and 1, 2, 3. It's all clockwise, by the way, opposite to the real engineering direction. That's positive, but electrical engineers, you know, they go with clocks, I guess. All right, these are all 1,000 ohms. So what is R sub A, R sub B, and R sub C going to be in a situation like this where we have a balanced loading on the Y connection, right? So what is so this is the Y to delta thing. We're just going to use our numbers that we've got here, and you're going to see how this all collapses down too. So let's do R sub A. Right? R sub A is R1 times R2. R1 times R2, that's 1,000 times 1,000, that's 1,000,000, right? 1,000,000 plus R1 times R3, R1 times R3, well, that's 1,000,000. Plus R2 times R3, well, that's a 1,000,000. So I've got 1,000,000 plus 1,000,000 plus 1,000,000, right? So I've got 3 times 10 to the 6. And what's my units? Well, it's ohms squared, isn't it? And then what I want to do is I want to divide that by R1. And R1, of course, is 1,000. So what does that give me? That gives me 3,000 ohms. So R sub A is 3,000 ohms. And by symmetry, we would see that R sub C is also 3,000 ohms. And R sub B is also 3,000 ohms, right? So equals R sub B equals R sub C. So what you can really see is if we say that R1 equals R2 equals R3, and this is what happens when all three of these are equal, and we call that R sub T. Right, we call that R sub T. And then we look over here and we see that R sub A has got to equal then R sub B, has got to equal R sub C, has got to equal R sub delta, right? And when we do that, we see that R delta equals 3 times R sub T. I probably should have used Y there instead of T, but because T sometimes stands for total. Let's call it a Y. R sub Y. All right. So that's just one thing that you want to think about, when you're looking at that balanced loading and everything else, is that there is a difference. And you're going to see that in your homework problems too. So I realized I didn't even put the timer on at all, or even think about putting it on, I guess. So I have no idea how long that took me. But what I want to point out is, this example. This is sort of an example that you can see. We're going to go through a more complex example in the next lecture, but the next lecture is going to not only finish this off with that example, but I'm also then going to go on into nodal analysis and start to talk about just easy, simple nodal analysis, and then harder nodal analysis, and we'll look at how you would do that both with using matrix operations as well as just using simple algebraic substitution if you can, right? Depends on how large of a dimension the problem is. All right. So I hope you have a good understanding now of delta to Y conversion and Y to delta conversion. It's going to be very important to you when and if you ever get into power electronics and large power electronics and connections along the transmission grid. And we have a lot of students, a lot of alumni who are working for National Grid. So you certainly may come up to Y delta conversions if you're working in the power industry for the rest of your life. All right. See you at the next lecture.